Hello, my name is Vitor with the Toyota Research Institute, and in this presentation I'll be talking about some of our latest developments in self-supervised learning for monocular depth estimation. Monocular depth estimation is the task of going from one single RGB image to a per pixel depth map. This is a new post-problem in computer vision, since there are infinite solutions to the lifting of 2D information into 3D space. However, recent developments in deep learning have enabled neural networks to leverage appearance-based cues and learn very accurate models capable of performing this mapping. In this work, we focus on the self-supervised setting, in which there are no ground truth depth labels at training time. Self-supervised methods use strong geometric priors to project information from one camera into another, and minimize an appearance-based photometric loss between image sequences. This training approach is highly scalable since it only requires video information, has a strong objective in the form of geometric priors, and leverages dense texture signal from every pixel in the image. However, it also has some challenges, which still limits its use in real applications. At CVPR this year, we presented Pacnet, a novel neural network designed specifically for self-supervised depth estimation. It uses novel packing and unpacking layers that preserve high-resolution information during the encoding and decoding stages. We showed that this new architecture scales better with number of parameters, image resolution, and longer depth ranges relative to the ResNet architecture. As a result, we established a new state-of-the-art in the task of self-supervised monocular depth estimation, outperforming previous methods by a large margin, especially when considering high-resolution images. Our results are even comparable with supervised methods, even though we only use videos at training time. These are some qualitative results of our proposed Pacnet architecture relative to the widely used MonoDepth 2, DORN, and the original SFM learner that serves as the starting point for the project. In our CVPR paper, we also demonstrate how weak velocity supervision can be used to produce scalar models in a self-supervised setting. We introduce a new loss on the magnitude of the predicted translation and show that as the post network becomes scalar, so does the depth network to maintain consistency, since both are optimized simultaneously via the photometric loss. We also developed several extensions on top of the our original work on Pacnet SFM to address some of the shortcomings inherent to the self-supervised learning of depth and ego motion. For example, at Core 2019, we presented a new two-stream pulse network that uses depth predictions as an extra input, and showed that by combining the output of these two streams, we can significantly improve visual odometry performance. Another work presented at the same conference involves semi-supervised depth learning, particularly under very sparse conditions. We introduce a new semi-supervised loss that reprojects depth estimation errors back to the image plane, so it operates in the same conditions as the photometric loss. We showed that our reprojected distance loss facilitates the training of models with very sparse labels, achieving state-of-the-art results with as few as 4 LiDAR beams as the only source of supervision. Another source of supervision we explored was information from a pre-trained semantic network. In our iClear 2020 paper, we introduced a novel depth estimation network in which semantic features are used to guide the generation of content-aware depth features using PixelAdaptive Convolutions. The ability to distinguish between different objects that are visually similar and generalize to similar objects that are visually different leads to further improvements in depth estimation, producing sharper boundaries and better delineation of far-away objects. We also introduced fine-grained depth metrics for different semantic categories, showing improvements in all of them using our proposed method. Another problem we address in the same paper is the infinite depth problem, a well-known limitation of self-supervised depth learning in which the network is unable to correctly model objects with no relative motion. We address this problem with a two-stage training strategy, in which frames exhibiting the infinite depth problem are automatically filtered out using a ground plane assumption, and then a second model is trained on this filtered dataset. Because it was not exposed to the infinite depth problem, the second model will not learn this behavior, and its resulting predictions will be correct. Recently, we also worked on self-supervised depth and ego motion learning with arbitrary camera models. Moving beyond the standard pinhole geometry, our proposed Nearrace surfaces is able to learn non-parametric projection models from any central camera, including highly distorted fisheye lenses and catadioptric systems. This non-parametric camera model is jointly learned with the depth and pulse networks from raw videos and is powerful enough to model frame-by-frame environment distortions, such as in underwater sequences. As a testbed for our experiments, we recently released a new dataset, DDADS, generated using data from our vehicle fleets with scenes collected in the United States and Japan. It includes 6 synchronized cameras and 4 luminar sensors, used to produce a 360 view at 10 Hz with corresponding ground truth projected depth maps with distances up to 250 meters. Training and inference code for our models, as well as the DDAD dataset, can be found at the following links. If there are any questions, please contact us. Thank you very much.